Welcome to chemistry classes. In this video we are going to discuss about color of coordination compound. Color of coordination compound, also we will discuss here metal carbonide. Okay, so here previous video we discussed crystal field splitting. Okay, so here we have to discuss color of coordination compound. We know coordination compound which consists of transition metal. Okay, coordination compound which contain transition metals from transition elements. They form different type of color. They form different type of colored complex. Clear? So here the major reason for this color, this is we are going to discuss here the color of coordination compound. Here when you pass a beam of light, okay, we know white light it contains 5 different colors. Okay, so when you pass a beam of light through a coordination compound, it will absorb some of the radiation from visible spectrum. Okay, so here you have to pass a beam of light through a coordination compound. Coordination compound will absorb some of the radiation from visible spectrum. Visible spectrum means VIBGYOR. Okay, from VIBGYOR some of the radiation will be absorbed. Then the coordination compound form a color. This color depends on the complementary color of light absorbed by coordination compound. Complementary color. So look here, you passed a beam of light through a coordination compound. The coordination compound absorbed some radiation from visible spectrum, visible region. Imagine this coordination compound absorbed radiation between 400 to 430. Coordination compound absorbed radiation, its wavelength between 400 to 430. So it's mean it absorbed violet color. Okay, coordination compound absorbed radiation correspond to violet color. Okay, then the coordination compound it will appear in yellow color. This is complementary color me. Okay, coordination compound absorbed violet color, then it will appear like yellow color. So the color of coordination compound is complementary color of light absorbed by coordination compound. Okay, coordination compound absorbed wavelength correspond to orange color, then the coordination compound appear blue color. Okay, that is mean complementary color. The color of coordination compound depends on the complementary color absorbed by the light absorbed by coordination compound. So this is a color wheel. This color wheel helps to understand color of coordination compound. In color wheel, this is color wheel, and here you can see here different color: violet, blue, green, yellow, orange, red. VIBGYOR. Okay, actually VIBGYOR 7 colors are there, but here we have violet, blue, green, yellow, orange, red. Okay, this color, there is no indigo. Here we have only these colors. Okay, and here the wavelength starting from here 400, 430, 490, 560, 600, 650 and 800. Clear? You have to remember this color and their wavelength. Okay, so here one question: a coordination compound absorbed a wavelength between 400 to 430. Then what will be the color of coordination compound? So using this you can predict its color. 400 to 430 mean it is violet color, so the color of coordination compound will be yellow color. Okay, similarly a coordination compound, it absorbed a radiation or wavelength between 600 to 650. coordination compound absorbed radiation between 600 to 650. Okay, 600 to 650 mean it is orange color. It is orange color. So its complementary color will be blue. So the coordination compound appear blue color. Okay, so this is coordination compound. So coordination compound mean compound which contain transition metal. They form different type of color. When we pass a beam of white light through coordination compound, it will absorb some of the radiation from visible spectrum. Okay, and the color of coordination compound will be complementary color of light absorbed by coordination compound. This color will helps to predict complementary color absorbed by coordination compound. Clear? Okay, next one we have to discuss here color of coordination compound based on crystal field theory. Color of coordination compound based on crystal field theory. Okay, so see here, this is one coordination compound. Here titanium with 6 water molecule. Okay, this is it is octahedral coordination compound. Six ligands are here, so it is octahedral coordination compound. Here central metal atom titanium atomic number 22. So here subshell electronic configuration will be like this, and outer shell electronic configuration it will be 3d2 4s2, 1s2 2s2 2p, 1s2 2s2 2p, 6 3s2 3p6 4s 3d. Okay, 3d 4s. When you write this at the end it will be 3d2 4s2, 3d2 4s2. Okay, this is for titanium. But in this coordination compound, titanium here it is 3 plus, titanium 3 plus. So you have to remove 3 electron, 2 electron from 4s and 1 electron from 3d. So 3d titanium 3 plus, its outer shell electronic configuration will be 3d1 4 0. So titanium 3 plus, there is only 1 electron in outer shell. Okay, so 3d1 d1, it is octahedral complex. We learned octahedral splitting like this, T2g Eg, 3 orbitals down and 2 orbitals up. Okay, this is octahedral coordinate, this is the octahedral splitting of coordination compound. Okay, and here d1 mean there will be 1 electron in T2g. Okay, this is electron filling in octahedral complex. Here only 1 electron, so no need to check about pairing. Okay, so here T2g 1 Eg 0. Okay, when we pass a light with a suitable frequency, this coordination compound absorb radiation. Okay, it is given here, it is violet color. This coordination compound violet color. Okay, so when you pass a beam of light, here the complementary color of violet, it is yellow. You can check color wheel. Okay, we discussed before. Okay, according to color wheel, here yellow color, when the coordination compound absorbed radiation corresponding yellow color, then this coordination compound appear in violet color. Okay, so after passing a radiation with a suitable frequency, this coordination compound absorb radiation corresponding to yellow region. Okay, also electron from this d1 electron, this electron here this electron from T2d, it will excite, it will move to Eg level. Okay, there will be a transition of electron will occur from T2g to Eg after passing a radiation with a suitable frequency. This 3d1 electron will excite from T2g to Eg. Okay, before it was T2g1 Eg0, T2g1 Eg0. Okay, in the beginning, after passing a suitable frequency radiation, it this electron moved from T to G to Eg. Now it is T to G 0 and Eg 1. Okay, this electron transition produce color. Okay, it absorbed a radiation from corresponding yellow region and there is a transition of electron. Okay, d electron from d subshell, there will be a transition occur and this transition called dd transition. Okay, this transition is called dd transition. dd transition we can represent like this, dd transition. dd transition mean here electron from lower energy, this is lower energy and this is higher energy. After receiving radiation with suitable frequency, electron transition occurs from lower energy to higher energy. In this case T to G to Eg. Okay, this transition produce color and this transition called dd transition. Okay, this dd transition is this transition of electron producing color, and this theory is, this is the application of crystal field theory. This is one of the application of crystal field theory. Okay, we know according to crystal field theory, we discuss crystal field splitting, octahedral splitting, tetrahedral splitting, T to G and Eg. These things are we discussed based on crystal field theory. Okay, so here crystal field theory is saying that there is a dd transition and this dd transition produce color. Okay, so here you understand here dd transition also complementary color. Okay, another thing you have to understand here, to produce color there must be ligands. Okay, without ligands transition metals do not produce color. Okay, there must be ligands to produce color. Look here copper sulfate, it is colorless. Copper sulfate with 5 water molecule, it is blue color. So here water molecule, it is ligand. In presence of ligand, it is blue color. Without ligands, it is colorless. Clear? So these are the things we have to discuss here. Okay, so here we discussed one coordination compound. Okay, this coordination compound violet color octahedral complex. Here it is titanium 3 plus, it is 3D 140, 3D140 mean it is T2G and Eg, T2G1 Eg0. After passing suitable frequency of light, one electron from T to G, it will excite to Eg. Okay, and here this coordination compound absorb radiation corresponding yellow color. That's why the coordination compound appeared in violet color. Transition of electron from T to G to Eg, it referred dd transition. Clear? Okay, next one we have to discuss here limitations of crystal field theory. So we discussed here crystal field theory, octahedral splitting, tetrahedral splitting, color of coordination compound. These things explained by crystal field theory. Okay, but there are some limitations. There are some limitations for crystal field theory. Here some assumptions in crystal field theory. Here in crystal field theory, ligands are considered like a point charge. Okay. Also in crystal field theory, according to crystal field theory, anionic ligands produce more splitting. According to crystal field theory, we know when ligands approach to d orbital, there will be a repulsion between negatively charged ligands and d orbital, and there will be splitting. This splitting called crystal field splitting. Okay, so according to crystal field splitting, according to crystal field theory, negatively charged ligands produce more splitting. But actually it is not like that. We know spectrochemical series. In spectrochemical series, we know halogens I minus, Br minus, Cl minus. Okay, these are lower end of spectrochemical series. Spectrochemical series mean arrangement of ligands according to their strong field and weak field, according to their ability, according to their strength of crystal field splitting. Ligands are arranged. Okay, so here these are negatively charged ligands and they produce less amount of splitting, and these are weak field ligands. But according to crystal field theory, negatively charged ligands, these are negatively charged ligands. According to crystal field theory, this type of ligands produce more splitting, but actually not like that. Okay, so these are some assumptions. Here ligands are considered like point charge, and according to crystal field theory, negatively charged ligands produce more splitting, but some in spectrochemical series, some of the negatively charged ligands are in lower end of spectrochemical series. They are weak field ligands. Clear? Okay, next one we have to discuss here bonding in metal carbonyl. Bonding in metal carbonyl. Metal carbonyl means it is coordination compound. It contains central metal atom and ligand carbonyl, CO. Okay, such type of coordination compounds are called metal carbonyl. Example for metal carbonyl: tetracarbonyl nickel. Tetracarbonyl nickel 0. Here nickel, its oxidation state 0. Okay, tetracarbonyl nickel mean nickel with a 4 carbonyl group. Okay, its structure will be tetrahedral structure. And another one, pentacarbonyl nickel. Pentacarbonyl nickel. Pentacarbonyl means there will be 5 CO group and it will be trigonal bipyramidal. Trigonal bipyramidal. Hexacarbonyl nickel. Hexacarbonyl nickel means there will be 6 carbonyl group. Okay, and it will be octahedral structure. 6 ligand octahedral, 5 ligand trigonal bipyramidal, 4 ligand it will be tetrahedral structure. Clear? So here homoleptic carbonyl compound means central metal atom and carbonyl group, ligand CO group only. Such type of carbonyl compounds are called homoleptic carbonyl compound, central metal atom and carbonyl group only, that is homoleptic carbonyl group. Okay, this type of homoleptic carbonyl group, they have well defined structure and these are simple compound. They are simple compound, they have well defined structure, and these are the different example for metal carbonyl. Okay, so here we discussed metal carbonyl. You can see here structure of metal carbonyl. Okay, different structure of metal carbonyl. Okay, so metal carbonyl here different type of bond, central metal atom metal and in carbonyl. Okay, carbonyl means CO group and there will be central metal atom. So here metal directly bonded to carbon. Okay, metal carbonyl means there will be central metal atom and carbonyl group. Okay, here central metal atom directly bonded to carbon. Clear? And here this metal carbon bond in metal carbonyl, they shows both the S character and P character. They shows both the S character and P character. Okay, and this metal carbon bond in metal carbonyl, they form two different type of bond, sigma bond and pi bond. Okay, metal carbon bond in metal carbonyl, they form this bond form two different type of bond. It formed two different type of bond, sigma bond and pi bond. Okay, sigma bond mean here sigma bond formed by donation of electron pair. Here CO, we know CO, it is ligand. This ligand donate electron pair to vacant d orbital of central metal atom, and here a sigma bond formed. Okay, So here we discussed in metal carbonyl, metal and carbon, they form two different type of bond, sigma bond and pi bond. How sigma bond formed? Carbonyl group, it contains lone pair electron. This lone pair electron will donate into vacant d orbital of central metal atom and form sigma bond. Okay, and look here how pi bond formed. Pi bond formed here metal carbonyl group. So metal which contain filled d orbital, metal it contains filled d orbital, and this filled d electron will donate into anti-bonding orbital of carbonyl group. Anti-bonding orbital we will represent pi star. Okay, so here metal carbonyl group, here metal which contain filled d electron, and this filled d electron will donate into anti-bonding orbital of carbonyl group or carbon group. Okay, and it helps to form pi bond. So here these are the things we have to understand about metal carbonyl group. Okay, metal carbonyl, here metal carbonyl, here first one discussed homoleptic carbonyl group means central metal atom and carbonyl group only. These are well defined. This type of compound, they have well defined structure and they are simple compound. Different example, metal, central metal atom and 4 carbonyl group, they are tetrahedral. Okay, example tetracarbonyl nickel, pentacarbonyl nickel, trigonal bipyramidal, hexacarbonyl nickel, it is octahedral structure. These are different example for metal carbonyl. In metal carbonyl, metal and carbon make bond. Okay, there are two different type of bond between metal and carbon, sigma bond and pi bond. Okay, here carbonyl group, it contains lone pair electron. This lone pair electron donate into vacant orbital of central metal atom and it helps to form sigma bond. Okay, similarly here some case central metal atom, it contains filled d electron. This filled d electron can donate into anti-bonding orbital of carbonyl group. Okay, and it helps to form pi bond between metal and carbon atom in metal carbonyl. Clear? Okay, so these are the things we discussed here. So another thing we have to discuss here, metal to ligand. Here bond between metal and carbonyl group. This bond between metal and carbonyl group, it produce a synergic effect. This synergic effect strengthen bond between metal and carbonyl group. Clear? Bond between metal and carbonyl group, this bond form a synergic effect. Okay, this synergic effect helps to strengthen bond between central metal atom and carbonyl group. Clear? Okay, next one we have to discuss here, stability of metal carbonyl, stability of coordination compound, or you can say stability of metal carbonyl compound. Okay, the stability of metal carbonyl compound depends on degree of dissociation of the compound in aqueous solution. Okay, so look here, degree of dissociation. Look here, imagine a coordination compound, metal with 4 ligand. How this compound formed? One central metal atom attached with 4 ligand and form a coordination compound. In aqueous solution, there will be a dissociation, degree of dissociation. It will ionize. Okay, the compound will ionize in aqueous solution. Clear? And here this is formed an equilibrium. Okay, so we know in equilibrium we can write here equilibrium constant. Okay, and here we will refer this equilibrium constant like stability constant. Okay, here a coordination compound central metal atom with 4 ligand formed by the addition of central metal atom and 4 ligand. In aqueous solution, it will ionize and it form an equilibrium. So we can write down their equilibrium constant, and this equilibrium constant we will refer here stability constant. Stability constant. Clear? So here this is one chemical reaction in which coordination compound formed. Okay, so look here metal and 4 ligand. So we can say this chemical reaction happened, in 4 different steps. Here first step, central metal atom attached with 1 ligand, it formed metal ligand. Okay, and here this is equilibrium. Okay, so we can write down their equilibrium constant K1 equal to so we can write down here K1 equal to metal, concentration of metal ligand. We know in equilibrium we will write concentration of product divided by concentration of reactant. So here this is product and here this is like reactant. Okay, so concentration of metal ligand, concentration of coordination compound divided by concentration of metal and concentration of ligand. Okay, so this is the first step. In second step, this metal ligand again reacting with another ligand, it formed Ml2, central metal atom and 2 ligand. Okay, and equilibrium constant for this reaction, it will be K2. Here it is K1, next one K2. Next step, Ml2, it will react with another ligand. Ml2 react with another ligand, it form Ml3. Okay, and equilibrium constant for this reaction, it is K3. Okay, Ml3, it is K3. Clear? And here last step, Ml3 react with another ligand, it form Ml4. And here equilibrium constant or stability constant for this fourth step K4. Okay, K4 equal to concentration of Ml4, divided by concentration of Ml3 into concentration of L. So this is a single reaction. This single reaction happened 4 different steps, and there are 4 different equilibrium constant, or there are 4 different stability constant K1, K2, K3, K4. 4 different stability constant. So consider this chemical reaction happened in a single step. So this is the equilibrium constant or stability constant for this chemical reaction, beta 4. Okay, beta 4 means concentration of Ml4, divided by concentration of M, concentration of N. And this 4 like power 4, concentration of L, power 4. Okay, so this is the stability constant for this single chemical reaction, beta 4. This reaction happened in 4 different steps. So 4 different steps, there are stability constant K1, K2, K3, K4. So we can say stability constant beta 4. This is overall reaction. Beta 4 equal to K1 time. Look here, all this you have to multiply, not add. Remember, not add, you have to multiply. Okay, this is the stability constant for overall reaction. So beta 4 will be equal to K1 times K2 times K3 times K4. Okay, this is the stability constant for overall reaction. Imagine there are 5 step or 6 step or unlimited step. Okay, imagine number n. So you can say beta n equal to K1 times K2 times K3 times etc. until n. Okay, if there is 10 step, so you have to do till K10. If there are 100 steps, so you have to do till K100, K1 times K2 times K3 times till K100. Okay, so generally we can say Kn. Clear. So here generally we will say the stability of metal carbonyl depends on the degree of dissociation of the compound in aqueous solution. Okay, the compound, imagine this is the formation of compound. Okay, and here we can write down the stability constant, just like the equilibrium constant we can write it. Okay, stability constant. Okay, and if there are several steps, we have to multiply stability constant of each step, then we will get stability constant for overall reaction. Clear? Okay, next one we have to discuss here important applications of coordination compound. There are many applications for coordination compound in our daily life. Okay, here we have to discuss some important applications of coordination compound. Okay, we know in chemical laboratory we will do some analysis, quantitative analysis or qualitative analysis. Okay, during this qualitative analysis, especially titration, we will use some reagents. Okay, so these reagents, some of these reagents are coordination compound. Example for such type of reagent, EDTA, ethylene diamine tetraacetate, EDTA, and dimethylglyoxime, okay, DMG, and another one alpha nitro beta naphthol, EDTA, dimethylglyoxime, okay, DMG. These are some example for reagent. These are some reagent it used for chemical analysis. Okay, and these are coordination compound. Okay, and another one extraction. Okay, extraction, isolation of metals, extraction of metals, purification of metals. Okay, previous chapter you discussed before. Okay, so during extraction or purification of metals also we will use some type of coordination compound. Example for such type of during the extraction of silver and gold, during extraction of silver and gold we will use Cn- as a ligand and it form coordination compound with silver and gold. Okay, during extraction of silver and gold, this silver and gold combined with the Cn- ligand, it form coordination compound. Clear? Also purification of metal, purification of metal through complex. Purification of some of the metals we have to pass through coordination compound. For example, during purification of nickel. Okay, during purification of nickel first changes to nickel tetracarbonyl nickel. Okay, so here this is coordination compound. So during purification of metal it form a coordination compound. During extraction of metal it form coordination compound. During chemical analysis some of the reagents are coordination compound. Examples are this. Okay, and another one in biological system, very important thing, biological system, we know chlorophyll, it is very important for photosynthesis for green plants. Okay, so chlorophyll it is one coordination compound. Okay, chlorophyll it is coordination compound, it contain metal magnesium. Okay, magnesium is the metal in chlorophyll and it is coordination compound. Okay, and hemoglobin, red blood cells. Okay, hemoglobin, it is coordination compound, it contain iron as a central metal atom, iron. Okay, and another one vitamin B12, it is coordination compound, it contain cobalt central metal atom. Chlorophyll, magnesium. Okay, chlorophyll, magnesium. And another one we discuss hemoglobin, iron, vitamin B12, cobalt. Okay, and some enzymes also coordination compound. Some of the enzymes are coordination compound. Clear? Also in black and white photography, silver bromide combined with the S2O3 Okay, silver bromide combined with the S2O3, it form a coordination compound. This type of coordination compound AgS2O3 twice 3 minus. This is coordination compound formed during black and white photography. Okay, here AgS2O3 twice, AgS2O3 twice 3 minus. Okay, which chemical helps to form this coordination compound? Silver bromide. Clear? So these are the important things, important applications of coordination compound, and these are the things we have to discuss in this chapter. Now this chapter is over. You can review all these points once again. So thank you for watching this channel.